So we used to use for potential energy the formula mgh, and this is only true when an object is on the surface of the planet and raised to a certain height h. But when an object is in space, then we will be using a different formula, which is, let me derive it for you. So if you have a planet, and let's say the planet's where you're raising an object to, the distance, all this distance from the center is r. And so you take an object and you rise to this height. The potential energy of it relative to the center of the planet, let's say Earth, is equal to the potential energy is the force acted on that object, which is the force of gravity, gmm over r squared, and times the distance you raised it away from the center, which is r. So one of the r's cancels, and you have the potential energy is equal to g m, the mass of the object, mass of the planet, over r. But then there is a negative sign right here that's appearing, and let me explain to you where the negative sign comes from. So if we have a planet and the planet has an object, if an object at infinity, there is not enough force acting on the object to bring it back to Earth or the planet. So the potential energy at the infinity is going to be equal to 0. In other words, when the distance is very high away from the center of the planet, the potential energy of the object is going to be equal to 0. Now, if I take my object and raise it from point 1 to point 2, at point 2, my potential energy is larger than at point 1. So the change of the potential energy must be positive. So I have the final, so this, I'm going to call it R, large one, and point 1, let me do it a little bit farther away so it makes sense. And this is little r, and this is big R. So the potential energy is the final, which is negative, and I have mm over r, or g, minus the initial, which is g. So I have to say minus, but it's a negative, that I have negative in my formula, and I have mm over, so final big R, right? Big R over little r. And so here you have this number is positive, and it is larger than this number, because your r is larger. When you divide by a bigger number, you get a smaller number. When you divide by a smaller number, you get the bigger number. So what you have is the positive number minus the negative number gives you the change of the potential energy, positive. So this is where and why this negative sign appears in the formula. In other words, if you took the object from 2 to 1, then you would lose potential energy and gain kinetic energy. So when you went from 2 to 1, you would get a negative change of the potential energy. But if you go from 1 to 2, you get a positive change of the potential energy. So in other words, when you use an object far away from the planet, and your potential energy changes with a different formula, which is the one that you see right here in the explanations in our lessons. But when the object is on the ground and close to Earth, then this little distance that you raise it above the ground is not that big difference. So there is change of the potential energy, but it's not that significant to look at. So the gravitational field around the planet at the smaller distances is the same. But if you look farther away, then the gravitational field is different here compared over here. So there's less gravitational field lines in this point than this one. So we have to use the new formula for potential energy when we look at the object farther away from the planet. Because your g farther away from the planet, your acceleration due to gravity farther away from the planet is not the same as it is close to the planet. So that's where this gravitational constant or universal gravitational constant appearing. And the negative sign explains like I explained how when you move farther away to the object, it loses potential energy, it gains potential energy, and when it gets closer, it loses potential energy. To keep that sign positive or negative correctly, you have to add that negative sign over there. Here's another concept that we're going to be dealing with in this lesson. It's the escape velocity, and we have to derive this escape velocity. I don't think this escape velocity is given to you in formula sheets on AP exam, so I'm going to derive in this escape velocity for you. So on the top of the planet, an object has gravitational and kinetic energy when you launch it off the planet. So its potential energy on Earth, and it will have some kinetic energy, and I'm going to call it escape energy. And then it will go far away to the point where it will stop, and its potential energy, like infinity, it escapes from the gravitational pull of the planet. Its potential energy far away is going to be equal to 0, and it's going to use all the energy that you gave and will stop eventually. So the kinetic energy of it is going to be equal to 0. So you have energy before it launched and energy far away at infinity when it is launched. So the potential energy has the formula of negative g, and I have the mass of the object, the mass of the planet, over r, and equals to the kinetic energy, which is 1/2, and this is r of the planet and mass of the planet, let's say Earth, and then equals to 1/2 m, and let me see, not equals to yet, so plus 1/2 mass, and this one is the escape velocity squared, equals to 0. And now I can set them equal to each other. Actually, the mass and the mass is going to be cancelled, and I have the v escape is equal to the square root of 2g mass of Earth over radius of Earth. So you see this formula right here given to you in the picture. So escape velocity for each planet is different and depends on the mass of the planet and the radius of the planet. For instance, escape velocity of Earth is equal to 11.19 kilometers per second. So if you can launch something at the velocity of 11.19 kilometers per second, it will escape Earth's pull. So if it's too slow, it will land on the planet. If it is a little bit faster but not enough to make a satellite, it will still land on the planet. You can give it velocity to where it will become a satellite, so it will just spin around the planet. But if you give it big enough velocity, then it will escape Earth's pull and be free from Earth, moving far away, not coming back to Earth. So that would be the escape velocity. So that was about the escape velocity concept that we have to know to solve these questions, and we also have to know about Kepler's laws. So for Kepler's laws, he came up with 3 different laws. One, he said that all satellites orbit in around planets or around stars in elliptical shapes. So let's say if it's Earth and it's orbiting Sun, then the Sun is going to be at one of the focal points of the ellipse. Like in the picture, you see that the Sun is at one of the points of elliptical shape. So if there is an elliptical, you always have 2 foci. So the Sun always is going to be in one, and just happens that most of the planets in our solar system, the shape of the motion for most of the planets in solar system is circular almost. So that would be the first rule. He said that the center of the orbital attraction point, like sun, would be in one of the foci of elliptical. So that's the first law. The second was that the radial line segment from the sun to the planet sweeps equal areas over the same time. So let's say it takes the same time sweep this area over the same time. It sweeps this area, and over the same time it will sweep another area, and these two areas will be equal to each other. So let's say if it took 1 hour to travel this distance, and it took 1 hour to travel this distance from this point to this point, and from this point to this point another hour, then these areas will be equal to each other, the one that I shaded. So that was his second rule. And the third rule is one of them, very interesting and used a lot. It states that the time it takes to move an object or a satellite around its the host center, like the Earth move around the sun, squared, so the time squared to move one rotation around the sun for Earth would be equal to, or would be proportional to the average distance between the sun and the Earth cubed. And in other words, this is how he derived it. He said that force of gravity is equal to the centripetal force, and the force of gravity is equal to the G mm over r squared, and the centripetal force is equal to m. The lowercase m is the mass of, let's say, Earth, and big M is the mass of the sun. That would be mv squared over r. So from here I can see that r and r can be cancelled, and m can be cancelled. So what I have is Gm over r is equal to, for v, if an object is moving in a circular motion, it's the distance it travels, which is circumference, 2 pi r, divided by the time it takes to make one revolution, which is the period. The period is, it takes the time to travel from this point all around back to the same point. So this time it's called period. So so the velocity of an object is the distance over the time, and the distance is circumference. So velocity squared will give me 2 pi r over the time, and all of it squared, because that's the velocity of the object moving in a circular motion. And if I square every single one term in this parenthesis, I get G m over r is equal to 4 pi squared r squared over t squared. I'm gonna cross multiply these guys, so I multiply this way, I multiply this way to get rid of the fraction, and I will get Gm t squared is equal to 4 pi squared r cubed. So in his third law, he said that the time it takes to make one revolution around this star for a planet squared would be proportional. So there is a proportionality symbol, or equals to, in this case, r cubed, the average distance of that planet from the star. On AP exam, they don't give you this formula again. You have to either remember this formula or this formula, but I think it's easier to just understand where the formula comes from so you can derive it. Let's look at this first question in this video. In Jules Verne's classic novel From the Earth to the Moon, a giant cannon dug into the Earth in Florida fired a spacecraft all the way to the moon. Mass of the Earth is, I'm going to round it to 16 to the 24 kilogram. If the spacecraft leaves the cannon at escape speed, at what speed is it moving when it is 1.5 10 to the 5th kilometers, so I have to convert it to meters, from the center of Earth. Neglect any friction effects. Radius of Earth is given 637 10 to the 3rd kilometers. Again, I have to convert to meters. Approximately what constant acceleration is needed to propel the spacecraft to escape speed through a cannon bore 1 kilometer long? So if we assume that the potential energy at the center of the planet is 0, then at the moment when the spacecraft is being launched, it has the kinetic energy, which is 1/2 the mass of the craft, and velocity, and then this is the initial velocity or escape velocity of the craft, and it has potential energy because it is the radius of Earth, the distance away from the center of Earth. So I have plus, and potential energy is negative g m of Earth, mass of the craft, and the radius of Earth. And then afterwards, because they're saying it is moving 1.5 10 to the 5th kilometers away from Earth, so it still has kinetic energy at that position, and they ask you what that velocity is. So I'm gonna call it mv final squared, so it still has kinetic energy, and now it has the potential energy of negative g, and I have the mass of the Earth, the mass of the craft, and this is the new distance. I'm gonna call it r. So the mass of the Earth is 598 10 to the 24. The new distance r is 1.5 10 to the 8, because I convert kilometers into meters, and the radius of Earth is 637 10 to the 6 meters if I convert it into meters. And because every single term here has a mass of the craft, then in your equation final velocity does not depend on the mass of the craft. So at first I times them all by 2, so I don't have a fraction, and I have, well, I still will have a fraction, but at least I don't have to deal with the 2. So I have initial velocity squared minus gm, and if I times it by 2, 2 appears on the top, and I have our Earth, and equals to, if I times the next term by 2, I only have v final, and that's the one I'm looking for, squared, and then I have minus 2gm, and then I have the final distance, the one that they asked me, the 1.5 10 to the 8. So if I'm solving for v final, I have v final is equal to the square root of, I have to move 2gm over r to the left side. So I have 2gm over r. Then I already had negative 2gm over r Earth. And I have initial velocity squared. I also could simplify. I see that both terms, there have, two terms have 2gm. So I could take 2g and m out, and then I have 1 over r minus 1 over re, and then initial velocity squared. Now if I plug in the numbers, the final velocity is equal to, I have 2 times g is 6.7 10 to the negative 11, times the mass of the Earth, I'm going to say 6 10 to the 24, 6 10 to the 24, and then the final distance is 1 over 1.5 10 to the 8, minus initial distance is 637 10 to the 3rd, 10 to the 6th, because it's kilometers. So I have minus v over re, which is 637 10 to the 6th, because it was kilometers, so it's 10 to the third in kilometers. And then I have escape velocity, but they don't give me what the escape velocity is, so I have to figure out what escape velocity is before I will be able to solve this problem. So let's calculate the escape velocity first. So for the escape velocity, I will say that all the kinetic energy is going to go to the potential energy, right? So if I say kinetic energy is 1/2 mv initial squared, and the potential energy is gmm over r, then if I solve for escape velocity, v escape velocity is equal to the square root of 2gm, and this one is the radius of the Earth, and this is the mass of the Earth. So if I plug in my numbers, I will get initial velocity, or escape velocity, is equal to, I get 11.23 kilometers an hour, or kilometers per second, and or 11.23 thousand meters per second. So I could plug in this velocity that I find into my equation, and that will give me the final velocity equals to. Always when I solve this type of questions, I don't like plugging in the whole thing into my equation. So what I did, I do partially. So then after I have this, so I don't skip the step because it's very easy to make a mistake with numbers that are this big and in the calculator. So now after I plug in, I will have my final velocity equals to. So here I got my final velocity at the end, after I did not skip my steps and plug in all the numbers that I have to find. So for the next question, they ask you to approximately what constant acceleration is needed to propel spacecraft to escape speed through a cannon that has 1 kilometer long. So the barrel that is 1 kilometer long. So now I'm gonna use the escape velocity that I just found. So this is my escape velocity, and they ask you about the acceleration. So you have force times the distance is the work, and equals to change of the kinetic energy of the object, and it goes from 0 to the escape velocity. So I have the force, which is the mass times acceleration, and equals to kinetic energy divided by the distance. So I have 1/2 mv escape velocity squared divided by the distance. So acceleration is going to be equal to mv squared escape. Oh, and the mass can cancel. So mass and mass can cancel, because I can set these two guys equal to each other. I don't care about the force anymore. So the mass is going to be cancelled, and I have my final expression for acceleration is 1/2 v squared over d. Now if I plug in my numbers, I get acceleration is equal to, let me plug in the numbers, it will be 63.06 kilo, because it's 10 to the third meters per second squared. Here's one more question, and I'll let you read it because I don't want to spend the last 6 minutes of the video on me reading the question. So go ahead, pause it, read it, and then after you read, let's solve it. So here's the information that is given. They tell you it is 24 hours, so I converted 24 hours into seconds. We just did the question where the radius of Earth was given 6.37 10 to the 6, and the mass of Earth was given 6 10 to the 24 kilogram. So every time you have, geosynchronous orbit, they mentioned geosynchronous orbit. Geosynchronous orbit, that means if you have our planet and there is a satellite, our planet is rotating and the satellite is rotating. This satellite is always looking at the same spot on Earth. So it's rotating at the same angular velocity as Earth is rotating. So every second it covers the same angle. So let's say if the Earth covered this angle, this satellite covers the same angle, not the same velocity, but the same angle within 1 second. So every time I have geosynchronous orbits, I'm gonna use my centripetal force is equal to gravitational force. So I'm gonna set it up as centripetal force equal gravitational force. I wrote the formula for both of them, and r is the distance, how far the satellite is placed. Also, I can cancel the mass of the satellite because my solution does not depend on the mass of the satellite. The capital M is the mass of Earth, and r is not the radius of Earth, but the radius at which the satellite is moving. Now I'm gonna, oh, and I cancel one of the r's as well. So I'm gonna simplify, and also I know that the velocity is equal to the circumference, the distance over the time, and the circumference is 2 pi r. This is the circumference at which the satellite is moving. And over the time is the period it takes. It takes 24 hours to go all around the Earth, looking at some same point. So I'm gonna plug it in instead of my velocity. So I'm gonna replace the velocity with this expression. So I changed the v squared for 4 pi squared r squared over t squared. I squared every single term in v. And now I'm gonna cross multiply and come up with Kepler's law, third law. So I got the equation for Kepler's law, where your radius of the orbit is equal to the third power, is proportional to the time it takes to go to around that orbit squared. Now, if I plug in all the numbers that are given, I will be able to find what r is equal to. Here's the big mistake that students usually make. They forget to take the cube root. So if I do the cube root, then I have all this expression, and now I'm gonna plug in the numbers and see what the radius is equal to. I got 7.610 to the 22nd, and sometimes it's complicated to enter this in your calculator. So what I'm gonna show you is like this. I'm gonna take one of the 22 to make the number larger, so it's gonna be 76, and then I have 10 to the 21, and the power of cube root is the same as 1/3. So now I'm gonna do the cube root of 70. So I have 76 to the power of 1/3, and times 10/21 to the power of 1/3. So my final answer for the radius is gonna be 4.24 times 10 to the 7. So when you take 21 to the power of 1/3, it's the same as multiplying by 1/3, gives you 7. And this one you have to take on your calculator to the power. You use this sign on the calculator to the power of 1/3. You probably want to take it in parentheses not to make a mistake. And that will give you meters. So that is the radius. This is how far the geosynchronous orbit would be for Earth. And then the next question, they ask you what is the orbital speed of the satellite. So I can use the velocity that I found the expression earlier to calculate that velocity. So the velocity is equal to 2 pi. I just found what r is equal to over the t, and time is 24 hours or 86,400 seconds. So I have 2, 3, 14. The radius I found 424, 10 to the 7, and the time in seconds, 24 hours, is 86,400 seconds. So if I plug in all these numbers, I will get 3.076 kilometers per second. So this would be the final answer for this question. So that's the velocity at which the satellite is moving on geosynchronous orbit. And I'm gonna stop here because I only have 30 minutes per video. So there will be more questions related to the potential energy, escape velocity, and maybe Kepler's laws in the future videos, and the links for the future videos to watch next in the description of this video.